Hello everybody, today is May 18th and we are going to continue on in our Kinetics and Equilibrium unit. If you recall, last week we talked about kinetics, and that is the study of rates of reaction, and that was a good review lesson for you from last fall. Today we're going to build on and talk about the concept of equilibrium. So, what is equilibrium? Equilibrium is the condition at which both the forward and reverse reactions occur at the same rate. So I have a simplified chemical reaction or physical reaction shown here. A reacts with B to yield C. And you're going to notice you could have the double arrow written this way or written this way. That means A and B are reacting to make C at the same rate as C is breaking down to become B and A. Equilibrium is always a dynamic state of balance between opposite processes. So we talk about this as the forward reaction, and this would be the reverse reaction. They're opposite processes. This means that the rate of forming reactants and products is equal. That does not mean that the quantities are necessarily equal, but the rate is equal. So in kinetics, we study the rates of reaction. When the rate of the forward reaction is the same rate as the reverse reaction, we can say that this system is at equilibrium. And it's very important to note that the system must be a closed system. That is, reactants and products cannot escape the system, or else equilibrium will not be achieved. Okay, so equilibrium can be broken down into two categories: physical equilibrium and chemical equilibrium. Let's first look at physical equilibrium. What this means is that when we have phase changes of the same substance, so in this case, like solid water is melting to become liquid water, and liquid water is solidifying to become solid water. This is a phase change, it's not a chemical change. And this is said to be at equilibrium. So we have that double-headed arrow here. And as a reminder, in the beginning of the school year, we looked at these heating and cooling curves. And in this case, we have a heating curve, and that solid and liquid dynamic equilibrium is occurring at this point in the curve. Just like the liquid and gaseous phase equilibrium is shown here. So the rate of melting is the same as the rate of freezing. Now let's look at physical equilibrium in terms of solutions. Well, if you recall, saturated solutions contain the maximum amount of solute per solvent at a given temperature. And saturated solutions are at equilibrium. So in this example, we've got sugar, table sugar in solid form. As it is dissolving in water, it's an aqueous solution. That is the forward reaction. At equilibrium, the reverse reaction, that recrystallization, occurs at the same rate. So dissolving and recrystallization occurs at the same rate. Another example, carbon dioxide gas. And carbon dioxide dissolved in water, an aqueous solution. This is what we have in a soda can or any carbonated beverage. It is at equilibrium. That gas is dissolving and the carbon dioxide is recrystallizing to become gas at the same rate. Okay, so let's move on to chemical equilibrium. Chemical equilibrium refers to chemical reactions. So you're going to have reactants breaking bonds and reforming bonds in a new, unique way to form products in chemical reactions. And we must note that the initial mixing of reactants has no products formed yet. So we always say that the forward reaction is favored. And here I have an example. And we used this example when we reviewed potential energy diagrams last week, so I thought I would continue with this. And I got this example from table I. So we have solid glucose, sugar, reacts with oxygen in gas phase to yield carbon dioxide, gas phase, water in liquid phase, and it also releases heat. So this is an exothermic reaction. When we first start this reaction, you only have glucose and oxygen. There are no products in the beginning. So this initial mixing favors the forward reaction. And we can show it here too. We favor the forward reaction. A plus B yields C plus D, or we can simply show A plus B yields C in this case. Another term I'll use is we're shifting to the right. When the forward reaction is favored, we are shifting to the right. And upcoming lessons will be using these terms a lot. Please note that over time, as products are made, the reverse reaction starts to increase. So again, we've got these reactants. They create products slowly. As products start colliding with each other, they can reverse that reaction and go, what we would say, favoring the reverse reaction, we shift left. So the products are now going back to create those original reactants. Now we can visualize this with this initial graph. So I'm going to have my reactants. Let's say this is glucose and oxygen. In the beginning of that reaction, you have a certain amount of these reactants, and as they collide and interact with each other, they start to decrease in amount. Why? Because we also have products being formed. So there were no products in the beginning, but products start to become formed. And in this case, it's CO2 and H2O. So that's in the beginning. Now, as equilibrium is achieved, it takes some time. So what we end up having is our reactants continue to decrease but reach a plateau. Our products continue to increase, but they also reach that plateau. And this represents this system at equilibrium. I could substitute any chemical reaction here that is in a closed system, and this would represent that equilibrium. The reactants decrease in amount as they form products increasing, and eventually the rate of reaction is equal. Not the amount of reactants and products, but the rate of the forward reaction is at the same rate as the reverse reaction. So that concludes my lesson for today. We are going to proceed tomorrow to talk about what happens when we stress these systems. And we can stress them by increasing or decreasing the temperature, increasing or decreasing pressure, and we can stress the system by increasing or decreasing the concentration. I hope you enjoyed the lesson today. Have a great day. Bye.